Hello again. We continue with our discussion of point pattern analysis. And in this set of slides, I'll talk about arguably one of the most famous statistics for point patterns, Ripley's K function. And I'll start by discussing the principle, which is essentially a move from first order moments to second order moments. Second order meaning variance and covariance counterparts for point patterns, and then the function itself and a few extensions. The principle is that the nearest neighbor distance only captures a partial aspect of the point pattern and not the full complexity. Specifically, it does not take into account interaction. Remember, when we spelled out the initial conditions for complete spatial randomness, it was not only equal probability for every location, but also that the fact that a point or an event actually is in one location does not affect the probability of having an event in other locations. So now we start focusing on that interaction between events. And so we'll construct a new function, the K function, which will capture that interaction, and we will either plot it as a cumulative density, which is the original K function, or as a density function, which is what is called a KD function. So first order intensity, which was the focus a couple of lectures ago, is the average number of points in a given area, which is similar to the notion of mean. In fact, we used this measure as the mean for the Poisson distribution when we wanted to calculate actual probabilities. So technically, mathematically, this is the number of points in a given small area dx. And we characterize this mathematically as what would this number be if this dx area becomes smaller and smaller. In other words, what is the limit value for this intensity? Of course, this is a pure mathematical abstraction. There is no such thing as points in an infinitely small area, but it is the idea of how to characterize the intensity of the process. And what we've already seen is for a homogeneous stationary process. Stationary is actually a term that is more rigorous than just homogeneous, because it pertains to the higher order moments as well. We've already seen that the intensity lambda is the same at every location, so it is a constant. Okay, keeping this analogy, so we were thinking about intensity as a first order moment, or the mean counterpart for a spatial point process, by thinking about how many points would be on average in an area that becomes smaller and smaller. Now, for second order intensity, we have two areas, dx and dy, that are a given distance apart. And we make those smaller and smaller. And so now we're interested in how many points would be in both of these over the product of these very small areas as these go to zero. So again, this is an abstraction. It measures how many points you can get between two in common, that are in two areas defined randomly on the space, and then to connect that back to the spatial distribution of the points, we'll connect that particular function to the distance between the two little areas, the dx and the dy. So this is a measure of covariance, if you can imagine it, for isotropic processes. These are processes without any complications, basically. Remember the pancake model. This cross-product measure only depends on the distance between the 2 points. And so I know this is a little abstract, and the way I like to translate it, if you wish, is to think about how many points you could find in a given area around another point. And so, given the distribution over space, now we're not focusing on what is the distance to the nearest point, but we're kind of flipping it around, if you wish, and say, okay, give a distance around a point, how many other points could we expect to be in there? And that gives an indirect measure of the interaction between the points. If there is positive interaction, we would expect more points to be there. If there is inhibition, we would expect fewer points to be in there. So it gets back to these very simple statistics of counting points within a given radius or counting points that are a given distance apart. But now the focus is on the second order moment. If this is all too abstract, just remember we're interested in interaction, so we're not just focusing on one distance to one other point, but we're focusing on all the other points within a given distance. And that's really what these second order statistics are about. They exploit this notion of covariance as the number of other points within a given radius, and they can be computed very simply by just counting how many points are within increasing distances and somehow summarizing that for the whole point pattern. And that, in fact, is exactly what the K function does. So Ripley's K function is arguably the best known second order statistic, but definitely the best known second order statistic, but also I think one of the best known statistics for point patterns. If you get any coverage of point patterns, this is probably in it. So technically it's called the reduced second order moment. This is a little obscure, but basically it's very simple actually. It is the expected number of points within a given radius of any point. And to make this comparable, we scale it by the inverse intensity. And why is this useful or necessary? Because otherwise, the denser the point process, of course, the more points you would expect in any given radius, everything else being the same. So this seems a little obscure the first time you see it, but it's there to correct for that and to make sure that these functions are comparable across point patterns. Now a little bit of math. What is the average number of points for? So we pick a given radius, let's say 1 mile, and then we compute it for 1 mile, and then for 2 miles we also compute it. But keep in mind that all the points that are within 1 mile are also within 2 miles. So it's really a cumulative statistic that it can't go down. You know, you cannot have fewer points in a 2 mile radius than you have in a 1 mile radius. At most, it's equal. If there's nothing between 1 and 2 miles, you have the same number as between in the 1 mile radius. So what is the average number of points? So we have a focal point I. We sum all the j's. I, this capital I here, is an indicator function, which means that if this condition holds, we count it. If it doesn't hold, we don't count it. So if for any given point j, the distance is less than our cutoff distance r, then I dij less than r is 1, and we count it. If it's not, it's 0, and we don't count it. And then since we have I as a given, there are n minus 1 other points that we need to consider in that. And so the average over all these other points is what we compute for each point I, and then we sum that over all the points. So we do this for every single point, and then correct, as I pointed out before, for the intensity. And intensity is number of points over area, so inverse intensity is area over number of points. So this expression here, with the area divided by n times n minus 1, and then this double sum, that is the estimate of the K function, which relates to the interaction of the process, the second order moment. How do you estimate it? You just do what the formula says. For each event, you have a given distance, let's say 1 mile, then you go to each point and look at how many other points are within 1 mile, and you count that. Then you go over all the points, you have all these numbers, you average them out and correct them for the intensity. And then you plot this function, which is a cumulative function, against the value of r. And as I mentioned before, it can't go down, so it increases. Now, I've alluded to these edge corrections in the previous lecture, and let me just say a few words. Technically, this gets pretty complicated, and you can find the details in the texts and in some of the readings, but the principle is actually very simple. So at the edge of a point pattern, there's a boundary, and we've seen early on the notion of a bounding box or a bounding polygon or a convex hull, but in essence that means that we treat the point pattern as if it's on an island, right? There is nothing outside. Now, in reality, that's not the case. So if in our examples that we've been using, for example, we have the supermarkets in Chicago, the way we treat this so far is as if there are no supermarkets outside the city of Chicago, which of course isn't true. So if you're interested in finding the nearest neighbor for a supermarket, say near the edge of the city, that nearest neighbor could very well be, say, in Evanston, north of Chicago or west of Chicago. But we don't have it. We have our mapped pattern, remember that term, which is all the points. We don't have the points outside. And so to kind of correct for the fact that this may be artificial, so in other words, if we have the nearest neighbor outside the bounds, then our measure of nearest neighbor will be too long because we're limited to taking the ones that are inside the bounds. So to correct for this, there are a number of different techniques, but they all boil down to the same thing, to basically mimicking what the point pattern might have been, since we don't observe it, outside the boundary. Now, in one case, it's the opposite. So the buffer measure actually creates a buffer at the edge and then only focuses on the points that are inside, so not in the buffer. And then you can find the nearest neighbors that might be in the buffer, and that, in a sense, corrects for the bias of ignoring points outside. Of course, the counterpart of this is that you lose all the points that are in the buffer, which, when you don't have a lot of data, is often not a good idea. So what other approaches do is kind of estimating or mimicking, simulating what points might have been outside given the pattern that you observe inside, and there's different ways of doing this. So you're artificially creating additional points in the pattern that you can then use to compute the statistics, like the nearest neighbor or how many points are within a given radius for the case statistic, counting points that are outside the boundary that you have artificially placed there as part of your edge correction. So that's what edge corrections are about. Inference for the K function, again, because we have this Poisson distribution, we know that K for any distance r will be pi r square. The lambda is gone because of correction. If we're above it, we have clustering. If we're below it, we have inhibition. Think about it. If we're above it, we have more points in our radius than we would expect under spatial randomness. So that's a denser point pattern, so that suggests clustering. If we have fewer points, that means they're pushed out more. That implies inhibition or divergent processes. And again, we can draw this line and then compare the one that we compute to that line, or we can use our simulation approach and get a randomization envelope, which we can then also plot. So for our supermarket example, this is the K function up here, and this is the theoretical under the Poisson. So we're above it, which suggests clustering of the supermarkets. With the randomization envelope, we have this gray zone here. Again, same principle as previously for the letter functions. We simulate many spatially random point processes and compute the statistic for each of those, and then stack them up for each given distance and take the maximum and minimum, or a given quantile like 95% and 5%. What does this look like under the three cases? Null hypothesis, we can see it from the randomization envelope, but this is a random process that I've simulated, and the black line, you see, stays very nicely within the randomization edges. Clustering, it's above. This is the same cluster process that I used before. And then a divergent process, it will be below. But you see, it's not totally below. After a given distance, it's not really that clear that it is that different from spatial randomness. So that is, in a nutshell, the principle behind the K function. It's a very nice summary of the overall pattern of the points, but again, it doesn't give us the clusters. Now, there have been many extensions and refinements of the K function. I'll just go over a few very quickly. We won't actually be using this in the lab, but you should be familiar with it in case you run into in the literature. So far we've focused on one point pattern, but we've seen before that there are multi-type point patterns, like the tree example, the Lansing Woods, where we had the different tree types in the same unit square. So we may be interested in the association between two, or lack of association between two different point patterns. The example I already mentioned was the study of the agglomeration of pharmaceuticals, where we had the pharmaceuticals and the preparers. So we might be interested in finding out, are they closer together than they would be randomly, or are they further apart? So it's the same idea. We focus on how many points of the other kind are within a given radius circle around a given point. So let's say we have the supermarkets and the liquor stores in Chicago. We might be interested in finding out, are supermarkets closer to liquor stores than they would be randomly, or are they, on the other hand, avoiding being close to liquor stores and try to stay away from them? That's a typical hypothesis. So the way you approach it is the same idea as I mentioned, but now you have one type of one process as the reference, and the points for the other process are the ones that you count in the circle. So that's the cross K function. There's different kinds of cross K functions for the process itself. For each process by itself, so that's the K11 and the K22, and then the K12 is for the interaction between the two. And under homogeneity, there should be no interaction whatsoever. There should be no correlation or covariance between them. And then we have our friend, the pi r square, again for complete spatial randomness. If the patterns tend to be more together than they would be randomly, it's the same idea. Think about it. So you have a supermarket and you count the number of liquor stores within a given radius. If you have more of them than you would under spatial randomness, that means, or that suggests, that the liquor stores would cluster around the supermarket, so that there is an interaction between the two. And you can also flip this around. Of course, the measure is not symmetric. And then if it's the other way around, if you have fewer liquor stores around the supermarket, then you would expect under spatial randomness, then it will be below the spatial randomness curve. And again, we have our randomization envelope. This is the example for the Chicago supermarkets relative to liquor stores. So here we have some evidence, some suggestion, since they are above the reference curve, we have some suggestion of association of clustering between these two types of stores. Another refinement of the K function, and in some textbooks this is actually given as the K function, but technically it's called the L function, is just a transformation of the K function, because the variance, so the K function, because it's an estimate from the data, is not an exact thing. It itself is random, and you see that very nicely when you do the simulation envelope. You know, if it would always be the same, there would be no randomness. But because of the randomness, even under complete spatial randomness, you get a different curve each time. Not very different, but a little bit different. But as it turns out, you know, as you increase the radius of the circle, the variability of that function increases. So it's in econometrics, you would call this a heteroscedastic process. The variance is not constant. So to make the variance constant, this BSAG's L function takes the square root of the K function divided by pi. And then you can plot this no longer against this, you know, exponential function that we computed from the Poisson, but because of the transformation, it becomes a diagonal. So you plot the LR function relative to the diagonal, or if you subtract R obviously from LR, you plot it against the horizontal. And this is a common plot that we'll see in a second. So interpretation, same as before. Why would it change? All you've done to the K function is take a square root and divide it by something. So you haven't changed anything to the relative positioning. If the L function is above R, its clustering is below its inhibition. It's a regular process. So here you see an example of this, again using our supermarkets. The standardized L function is here, and the null is pretty much a horizontal with the randomization envelope around it. So the L function, basically the same as the K function, just rescaled. Be careful, in some textbooks the distinction between the two is not made explicit, and sometimes the K function is actually presented, the L function is presented as if it was the K function, which it sort of is, but not exactly. And then finally, as I mentioned early on, a different approach is to take the same idea, is to take these, you know, counts of points within a given radius, but instead of looking at the cumulative distribution, you look at the density function, which you can technically compute using a kernel procedure, some smoothing procedure. And this is the KD function. We won't actually be using it, but I do want you to know that it exists, and it was actually used in that example in economic geography by Duranton and Overman, looking at the pharmaceutical, at the manufacturing distributions. And this just looks a little bit different, but it's again a randomization envelope. We have above the envelope clustering, below the envelope inhibition. One thing that Duranton and Overman introduce is to use potentially other reference distributions than CSR. So the idea is that you just simulate that other distribution and then create a randomization envelope for it, and then compare your actual density function to that envelope. And so they all look the same. In the case of the liquor stores, we actually don't find a lot of evidence of clustering. It's pretty much, there's a little bit of clustering, maybe at very small distances, but other than that, there's really not too much there. So this concludes my very cursory treatment of the K function. I did want you to know about it because it's so commonly cited and used. But the important concept here is that rather than focusing on a first moment, the intensity, now we focus on the notion of interaction, covariance, correlation, which is a second order moment. And so rather than taking the nearest neighbor distance or something similar to that, we look at the number of points within a given radius and how that changes with the distance that separates these points. And that's the principle behind the K function. As I mentioned, the K function is about the global characteristics of the pattern. And next, we'll focus on the local K function and an alternative perspective as reflected in the local joint count statistic. See you then.